Okay, we'll look at a bilging problem. Box-shaped vessel bilged at the end. In this instance, it's the forward end. It won't really make much difference whether it's forward or after end. We're given a length, breadth and draft, kg, and there's an empty forward end compartment, 22 metres long, which extends over the full breadth. And we have a watertight flat 4 metres above the keel. So that's an important point to consider when we have a watertight flat. Because looking at the sketch, 140 by 24 by 5.4, the waterplane area is definitely intact. Therefore the LCF doesn't change, it's at 70. And the waterplane area is definitely intact because the waterline is intact. So before we're bilged, LCG, LCB in line. And what will happen is, after we become bilged, the longitudinal centre of buoyancy moves aft by the distance we're going to calculate. Once it moves apart from the LCG, it creates a lever, and if we multiply that lever by the displacement of the vessel, that gives us our trimming moments. So looking at the problem, always calculate the sinkage first in any bilging problem, and we get 0.629. Add that to the draft, that gives us our new draft. And as I just mentioned, the LCB has now moved away from the same position as the LCG as a result of being bilged. The compartment lost does not cover the whole section of the bilged length. In other words, we've still got this part here that's underwater volume, therefore we would class it as non-symmetrical. So we're now required to calculate the distance of the LCB has moved aft. So we include the whole underwater volume after being bilged, multiplied by the centre of buoyancy, which creates the moments. Let's then take off the bilge compartment, and its distance we use is 129 because the length is 140, so from aft to the centre here is going to be 140 minus half of 22, which gives us the 129. LCB is the moments divided by volume, 63.134. So the distance the LCB moves, simply subtract that from 70, 6.866, and the trim moments created will be the distance multiplied by the displacement, not forgetting to use the density. So we've got our moments, so to create the trim we need our MCTC. And there's the formula for MCTC. Obviously the displacement doesn't change, the length doesn't change. GML is km minus kg. The kg doesn't change because our displacement doesn't change. Therefore we need the KML, which is KB plus BML. And the KB, now because we haven't lost the whole of the front part of the vessel, we cannot simply divide the new draft by 2. So we have to take into account the fact that we do have remaining underwater volume there. So again, it's 140 by 24 by 6.029, again using the whole value. Multiply that by the kg, which is KB, which is half the 6.029. Then take off the compartment. Again, its centre will be 2. And that gives us a KB of 3.133. BML, BL cubed. Notice that the L is the full 140 because our waterplane area is intact. And that gives us a GML of 301.3. We can now use that in the formula to get our MCTC. Once we have that, of course, we can find our trim, 319 centimetres or 3.19. Because our centre of flotation hasn't changed, it will change the draft an equal amount forward and aft. So I've written there my initial drafts, sinkage, and then my change due to the change of trim to get the final drafts.